Hey everyone, and welcome to The Explainer. Today, we're going on a seriously fascinating journey. We're going to trace the complete life cycle of a signal. We'll follow it from a very moment it's captured in the darkest depths of the ocean. Watch how it gets filtered through some incredibly advanced mathematical models. And finally, see how those complex findings are synthesized into actual actionable insights that engineers use every day. If you love figuring out the invisible mechanics of our world, you are absolutely going to love this one. But first, I want you to imagine a scenario. Picture yourself standing in the middle of a massive, echoing concrete hall. There are hundreds of people talking at once, heavy machinery humming in the background, air conditioning units just roaring. Now your job is to isolate and listen to a single whisper coming from someone standing all the way on the opposite end of the room. Sounds literally impossible, right? Well, that is exactly the problem marine engineers face when they're trying to detect modern submarines and quiet ships out in the massive, chaotic expanse of the ocean. How do they hear the undetectable? Here is our roadmap for making sense of this today. First, detecting the undetectable. Second, how MEMS listeners work. Third, virtual sensing and SHM. Fourth, the Kalman versus Gaussian process. And finally, extracting engineering insights. Section 1. Detecting the undetectable, the challenge of stealthy acoustic signals. Okay, let's dive right into the physical world of ocean monitoring. We've got a massive headache on our hands thanks to modern acoustic stealth technology. Now, for decades, listening to ships was pretty straightforward, honestly, because they were loud. But today, acoustic stealth tech is so good that the radiated noise from modern ships and underwater vehicles has been drastically reduced. They essentially just blend right into the natural background noise of the ocean. This isn't just a tactical defense issue, it's a huge challenge for basic marine environmental monitoring, too. Engineers quickly realized they couldn't just use a more sensitive microphone to hear these quiet ships. They needed an entirely new method with incredibly high spatial gain just to capture the data. To really grasp the hurdle here, we gotta talk about SNR, or signal-to-noise ratio. Simply put, this is just the ratio of the strength of your desired signal, so the ship you're trying to hear, compared to the background noise, which is just the random ambient sound of the ocean. When the background noise is louder than your target, your SNR is terrible. Your target is entirely buried in the noise. Finding a way to boost this SNR was the massive breakthrough a brilliant team of researchers recently achieved. Section 2. How MEMS listeners work. Listening in 2 dimensions. So how exactly did they solve this low SNR problem in deep water? Well, they redesigned the listener from the ground up. They moved completely away from traditional microphones to something microscopic and highly advanced. Traditional hydrophones are essentially just underwater microphones. They measure scalar sound pressure, meaning they only tell you how loud the pressure wave is at a single specific point. But the new MEMS vector sensor? It does something incredibly clever. It measures both the sound pressure and the vibration velocity of the water particles. Because it captures the direction and the speed of the vibrating water, the sensor can actually actively suppress the isotropic background noise, that's all the random noise coming from every direction, and focus directly on the source. The hardware making this happen is just fascinating. The sensor uses a bionic, cap-shaped cilia structure. Think of tiny microscopic hairs, kind of like the ones inside the human ear, that physically bend and sway with the acoustic waves. It features 2 vector channels to grab that directional data and 1 standard acoustic pressure channel. It's pulling in all this information at a staggering 40,000 samples per second. And the best part? Despite being a low-cost, super compact piece of micro-electromechanical tech, which is what MEMS stands for, it can run continuously underwater for 48 hours on a single battery. And this brilliantly illustrates the impact of that design. 10 decibels. By successfully canceling out that omnidirectional ocean noise, the MEMS vector sensor achieved a massive 10 decibel gain over traditional sound pressure methods. In the acoustics world, a 10 dB gain is absolutely monumental. It is quite literally the difference between completely losing a target in the static and hearing it loud and clear. You really see how this plays out across different frequencies too. Whether we're looking at the 200 Hz, 500 Hz, or 1000 Hz low-frequency bands, the MEMS sound intensity method consistently and dramatically outperforms traditional pressure sensing. It's actively isolating that target signal from the overwhelming noise of the deep ocean, no matter the frequency band. But look, lab results are one thing, right? To prove this actually worked in the wild, researchers deployed the listener 35 meters deep into the Fenhae No-2 reservoir, and in a real-world test, it successfully detected and isolated the radiated noise of a very small, quiet traffic ship driving back and forth over 173 meters away. The technology definitively proved it could reliably pull the acoustic needle out of the haystack.
Section 3. Virtual Sensing and SHM. From physical water to digital structures.
Now, let's zoom out a bit from the physical hardware sitting at the bottom of a reservoir. We need to look at the digital software algorithms required to actually make sense of all this mechanical data. Because we have to ask ourselves, what actually happens once the sensor captures that raw data? A massive string of numbers representing 40,000 samples every single second isn't inherently useful to an engineer or a doctor. Without context, it's really just more noise. And that brings us to structural health monitoring, or SHM. It doesn't matter if you're monitoring the vibrations of a stealth ship's hull or tracking the blood pressure inside a highly delicate medical device. Raw vibration and pressure data is utterly useless without algorithmic filtering. SHM uses virtual sensing, processing these massive high-frequency sampling rates like 25.6 kilohertz to constantly monitor the actual structural integrity and health of a system. Section 4. Kalman versus Gaussian process, filtering the digital noise. To process that kind of a high-frequency data firehose, you have to run it through mathematical filters. In the engineering world, there are two specific Bayesian-based approaches that teams heavily rely on to clean up structural health data. The crucial thing here is just understanding what each algorithm actually brings to the table. First, you have the Kalman filter. Think of this as your real-time workhorse. It is constantly predicting the next state of the system and filtering out sensor noise on the fly, which makes it absolutely perfect for real-time continuous monitoring. Then you have the Gaussian process. This one is heavier. It's used for regression and generalized prediction. So if you've got a highly complex system and you need to analyze its behavior across, let's say, 50 different configurations to predict future states, you're going to use a Gaussian process. The real-world stakes of these algorithms are massive. By analyzing things like mean squared errors and time responses, they literally keep vital systems running safely. In the medical field, these exact types of algorithms are applied to vibration and pressure sensors to reliably monitor critical human metrics like heartbeat rates and blood pressure, all without triggering false alarms. In engineering, they analyze the brake and beam systems of massive structures to accurately predict structural degradation over time. They take raw, chaotic noise and turn it into a crystal clear picture of health. Section 5. Extracting engineering insights, synthesizing data into knowledge. Let's zoom